Hello, in this lab, I investigated the motion of the objects moving at constant speed in one dimension. The purpose of this lab is to test whether the motion at constant velocity can be accurately described by a computational model. This is done by comparing the motion of a dynamic cart in real life with a computational model using GlowScript. The computational model relies on Newton's second law to describe the motion of an object where the net force acting on it is equal to zero. The result of the test determined that the computational model did successfully replicate an object moving at constant motion, given that the motion it described matched the motion of the dynamic cart in real life. The system I analyzed is the cart. The surroundings include the floor, the earth, the air, which interacted with the cart through normal force, gravity, friction, and air resistance. To collect data, I pushed the dynamic cart across a track. There was a built-in mirror on the side of the track, which was used to measure the position of the cart. I kept the camera fixed and perpendicular to the direction of motion. The cart moved and then pushed the cart, which moved horizontally across the screen. In Tracker, I calibrated the scale using the dynamic cart's track, which was 2 meters. I defined the x-axis to be the direction of motion along the track. Then I tracked the position of the front of the cart, frame by frame, to obtain its position versus time data. I started tracking from the moment that the hand pushing the car was no longer in contact with the car, which meant that the hand was no longer exerting a force onto the car. The resulting position versus time graph appeared linear, indicating constant velocity. The motion that describes the dynamic cart can be explained using Newton's second law, which says that the net force is equal to mass times net acceleration. For constant motion, the acceleration must equal to zero, which means that the net force acting on the cart must equal to zero. Some vertical forces that act on the cart include gravitational force which acts downward, and normal force, which acts upward. However, since both of these forces are equal in magnitude and are opposite in direction, they cancel out. Thus, the cart does not accelerate up or down. Moreover, on the horizontal side, the constant velocity shown in the motion means that small resistances such as friction or air resistance cause a negligible change in velocity, so it can be assumed that the horizontal net force is also equal to zero. To make the computational model, I use the momentum principle, which says that final momentum is equal to initial momentum plus F net times t. Since F net equals zero, it would indicate the momentum is constant, and that is equal to m times mass times velocity. This means that I can model the motion of the cart using the function of position, using a function of position as a function of time, where x of t equals initial position plus v times t. Here, v is which is the initial velocity, is obtained by measuring the slope of the graph, which was obtained from the tracker. This model assumes that net force equals zero, there's no acceleration, there's constant mass, and that the motion is one-dimensional. After comparing the graph of the computational model versus the data, both plots appear to be linear and closely overlap with a similar slope. This agreement shows the assumption that net force correctly describes the motion, and that the computational model does pretty accurately describe the real-life motion of the dynamic cart at constant velocity. Small differences might occur due to slight tracking errors, frame rate limitations, or minor resistance forces such as friction or air resistance. Overall, both graphs are thoroughly similar, which is able to justify the accuracy of the computational model. Now, if I flip the axis direction where plus x and negative x were interchanged, all position values would simply change sign since the direction has changed. And same goes for the velocity, where the sign would change. However, the magnitude would remain the same, and the motion would still be constant velocity. The acceleration would still be zero, and the net force is zero. This is because the physics still remains the same. Flipping the axes simply means setting the left direction equal to positive rather than the right. Since net force is zero, all the other factors would still remain the same, and alternating the negative x, interchanging negative x and positive x, would simply change the signs of the velocity. Errors in this experiment may include calibration uncertainty, slight camera misalignment, and as well as not contemplating maybe small differences in the velocity or position that may have been caused by resistances such as friction or air resistance. However, in conclusion, the observed motion still matches the predicted Newton's second law, where net force is equal to zero, and the computational model successfully reproduced the experimental data of the dynamic cart in real life.